Okay, so last time we mentioned that if we want to look at a material and see its properties, we have to make sure that we're normalizing it. We're normalizing it so we're not just looking at, well, a big pole can take more force than a small pole. We don't want that. So instead of looking at force, we look at stress, which is kind of like normalized force. There was definitely no writing there a second ago. Okay, so stress is equal to that force over area. We are dividing by the cross-sectional area, or the area that's going to be cut, to show how the material acts under these conditions. But how do we measure this? Because we want to see how it performs, we're trying to figure out how it's going to deform, how it's going to change, when it's going to break, and how do we test that? Well, now that we have this nice normalized system, we're going to put it into a tensile test machine. So we'll have an extensometer, which says, okay, this is how much it has stretched. We'll have our specimen, and it'll have a known length and known section. All of this right here is set in stone. So we have that reduced section starts at 2¼ inches. We have a gauge length of 2 inches, a diameter of 0.505 inches. The fillets are set, and the end diameters are also set. All of that is known. And so you add a load, you see how much it stretches and how much the diameter changes. And you keep on going. So when you do that, you're going to see a few things. And well, I'll get to that a little later. For now, let's look at this right here. So we say that stress is force over area naught. That naught's important because it's saying that when we're measuring stress, we're always saying it's the original cross-section. And for shear stress, we're also saying it's the original cross-section. However, when you stretch something, it's going to get thinner in the middle. So honestly, the stress will increase based on that force. You'll be applying a force, but you'll have a smaller area. So stress actually increases more than this equation accounts for. But how do we determine how much it deforms, how much it changes, how much it stretches and strains? We do it by defining another term. Just like we had to normalize our force by dividing by area, we also need to normalize the deformation. How much did you change in size? Well, you could just say, well, my deformation, which is usually given with the delta, is equal to 5 millimeters. But that's very impressive if its original length was, 10 millimeters. Like, wow, that was quite a ability to stretch. And it's less impressive if the original length was equal to 5 miles. Okay, didn't really do much. So just like we normalized by the area before, we probably want to normalize by our original length to get a better idea of what's happening. And that's what we're doing here. We're looking at the change in length over our original length, and it gives us something called the strain. Now, for stress, we had units of megapascals. You can see that on the previous slide, right here. And we're using a very fun little conversion here for most of your problems, which is that a megapascal is either 1,000,000 newton per meter squared, or it's equal to 1 Newton per millimeter squared. Remember this conversion? It's a very, very helpful one. That's equal to a megapascal. But our strain does not have those same units. Our strain is unitless because we have length over length. The units cancel. So a lot of people just refer to it as strains, but just know it's a fraction, it's a number. Okay, then we have various types of strain here. We have the tensile strain, which comes from our tensile force. That's changing the length. And we have our lateral strain, which is going to be the change in the diameter, or the lateral dimension. It's like rectangular. And then we also have the shear strain, which is simply going to be, I have a force, it's being applied in this direction. What is the change in position from my original location to this point? How much have I moved from this original location to this point? And that's going to be delta x. And I have my original side length, which is y. And then your shear strain is going to be equal to tan of that little small angle. If it's a small enough angle, you can just say it's equal to theta as long as you're in radians. However, that's only for small angles, so why take that chance? And you can just do tan theta. It's not that hard for you to calculate. Okay, so in this time we have introduced our strain and shear strain. Remember that they are unit list. So you will sometimes see strain referred to in radians, which is kind of a placeholder more than a unit. You'll sometimes see our regular strain termed as strains. Either way, don't worry about it. What are they? They're a change in a dimension over the original dimension. In this case, it's going to be tan of that angle. So it's how much the angle has moved from 90 degrees. How much has the angle changed from 90 degrees? This is important because it's how we look at deformation. Okay, so we've learned about stress. We now know that stress causes strain. And we're going to keep on going from here and learn how all these things get connected.